The topic I want to discuss today is how machine learning and, in general, computer techniques can help us to improve our detectors, not really from the point of view of data analysis or being better at detecting signal, but being better at making our instruments more robust and less noisy. So yesterday, Jenny gave already a very good introduction on how our detectors are working and how they are controlled. So I don't have to spend too much time on this, but I still want to give you a brief introduction just to refresh the ideas, and also to give a point to give it an introduction of how to control the detectors from the point of view that is useful for the rest of the talk. So as you know, advanced gravitational wave detectors are laser interferometers. So you've already seen different variation of this scheme in the previous day. But the idea is that you have 4 main test masses that you want to monitor the distance between those test masses to check the changes in distance generated by gravitational waves. And this is as far as I will go in using general relativity of knowledge of gravitational waves. So to reach the very low sensitivities that you need to detect gravitational waves, you have to use a bunch of tricks. So instead of having a simple microinterferometer, you have to add a lot of resonant cavities that are able to enhance the sensitivity of the instrument. But of course, you have to pay some prices. And the price you have to pay is that the complexity of the system increases significantly. And also, all the tricks works only when the distances between the mirrors, so the length, degrees of freedom of your systems, and the angular degrees of freedom of your systems, are kept very, very close to the resonant condition, to the operating point. So to do that, as Jenny mentioned yesterday, we have to implement hundreds of different feedback control systems that continuously monitor variations of the physical degrees of freedom that are relevant to maintain your system in operation. They monitor variation of those degrees of freedom, and they act back by pushing on the proper mirrors to maintain the system on resonance. To be able to reach the sensitivity we need, we cannot really use any macroscopic of local measurement of the position of the mirrors. We really need to rely on optical signals, so signals that are extracted from our lasers, to measure the relative distance between the different mirrors. And so the techniques we use is essentially a radio frequency modulation, demodulation schemes, but this doesn't really matter too much at this point what this technique is. The key here is that it is a very efficient and sensitive way of measuring the motion of the system degrees of freedom only when the system is already very close to the proper operating point. In other terms, the linear range where the signals respond linearly to motions of systems is extremely small. It's hard to really make a proper estimate, but for a full interferometer, only like advanced LIGO, only considering the longitudinal degrees of freedom, there are 5 degrees of freedom there, the fraction of the total phase space where the mirrors can move, where we actually can extract linear control signals, is less than 10 to the minus 9 or something of that order of the total volume. So this means that you can't possibly sit there and wait for the system to naturally, because the random motion, get into that regional space, because you would probably wait forever. And the point is that all the mirrors are suspended to a complex seismic isolation system, as we already mentioned yesterday, with the goal of reducing their motion at high frequencies above 10 Hertz. But again, how much the mirrors move at low frequencies, so on a time scale of a few seconds or something like that, is of many microns, so way more than the size of where the linear signals are available. And so you need actually to find a way to go from the initial completely random motion of the system, somehow drive it to the high sensitivity condition, which is where all the degrees of freedom are around 0, where 0 we define the operating point. So the problem here is a problem of having a system which has a dynamic which is linear because the suspension is a very linear system, but because of the seismic motion involved, because of the seismic isolation, has a very long memory. You can't really predict how the mirror is going to move unless you know what happened in the past 1 or 10 seconds, even more than that. On the other hand, the readout of your system is highly nonlinear, meaning that you don't have a direct way to measure every time, everywhere, the state of your system, in the sense the position of the mirrors, but you only have a highly nonlinear readout of the position of the system. So this is a typical example of a problem of nonlinear control, in where even though the dynamic is linear, actually your ability to measure the state of the system is a nonlinear function of the state itself. The complexity here added on top of it is that you really also need to track what happened to the system over quite a long time, order of seconds, because of the long memory in the dynamics. So here's to give you a little bit of an idea of what kind of control and sensing problem we have. So I'd like to distinguish now two different regimes in the operation of our detector. The first one is what I mentioned just earlier. So what we call the lock acquisition. So basically it's to find a way to drive the system from the initially uncontrolled condition when all the mirrors are swinging around like crazy. Of course, all is relative. They're swinging around by a couple of microns, but it's still way more than what we need. And so we need to find a way to efficiently drive the system close to the operating point and then keep it there. So this is a nonlinear control problem, as I just mentioned. It's what we call the lock acquisition. Then once we get there, we are in what I would call the high sensitivity operation. So at this point, the system is kept by the feedback loop near the operating point. So it's very well described as a linear system. And as mentioned also yesterday, it is operated as a null detector in the sense that the feedback are keeping the system around zero. And so at the end, you need to calibrate the gravitational wave strain out of both the residual deviation and the force you apply to maintain the system there. So as I said, this is almost a linear system, but remember that we have very demanding requirements for our sensitivity. So even small deviation from linearities are important. So I would like now in the rest of the talk to try to give you an idea of how machine learning could be used or has been used to tackle problems in those two cases. So let me start with lock acquisition, which is the one where there aren't really many results, but just to give an idea of what we could do. So first of all, let me try to convince you why it is interesting to do this. So as I said, we have 5 longitudinal degrees of freedom, just restricting to the, let's say, a relatively simple problem. And we have tens of signals that are derived from the optical sensor. Again, we have a readout of all the degrees of freedom that are mixed, and the response of those signals for most of the phase space is nonlinear. So the current approach for lock acquisition is based on triggering power levels using auxiliary lasers. It's a complex system that has been developed over years by trial and error, and is based on experience and a lot of historical reason why things are done that way. It works, but it can definitely be improved. It's nowhere close any optimal strategy. So you might ask, if this thing is working, why do you need to improve? Well, so if you look at the typical downtime during the last science run of one of our detector, you see that it was observing for about 72% of the time, and 12% of this time is in this state which is called locking, which means it's in this state where we are trying to recover from a completely uncontrolled system and go back in high sensitivity. So it is, of course, useful and interesting to reduce this fraction. Right now, it takes about 20 to 30 minutes to go from an uncontrolled state to a controlled state. So if we can reduce this, we have a direct science payoff, because 12% of downtime over all the GWTC3 times, or all of O3, means 12% of 90 events, which is about 11 events that we might have missed just because we were not observing during that time, because we were trying to recover the high sensitivity operation of the detector. So it is useful and interesting to improve this, to find new ways to do the lock acquisition, because we might just have more uptime. And also the current configuration is not really easily scalable to more complex and future interferometer configuration. So it would be ideal to have a more deterministic and a more systematic approach to the local position. So how can machine learning help for this? Well, so the typical approach in machine learning for what concerns controlling system is reinforcement learning. So the idea of reinforcement learning, for those of you that are not really familiar to it, is that you have some sort of a machine learning agent which directly go and poke your physical system, trying different kind of policies of how to actuate on your system, trying to build up a planning strategy based on the signals it can read out of the system, and building a policy that then they give you some sort of rules to act on the system to try to maximize some sort of reward. And in our case, the reward would be how fast you can get to the high sensitivity condition or how long you can keep the system there. So this seems very interesting, and the pros is that it could be completely model agnostic. People have typically trained the reinforcement learning system to learn to do tasks from scratch without any previous knowledge of what was going on. But of course, if you have some model knowledge, you could use the model knowledge, the knowledge of your system, and then you can even improve your knowledge with reinforcement learning. The cons of this approach is that it's extremely time-consuming because typically you need many, many attempts on a real system to learn. By many, I mean millions. The typical amount of times a reinforcement learning agent have to play with your system is of the order of millions of times or something like that. And of course, it's kind of so we can't really afford to have this happen in real time on the real system because it's extremely expensive, not only from the scientific point of view, but also from a really monetary point of view. And also you want to be careful because random policies at the beginning could perform unwanted action on the system that even though they might not break the system because there are safeties there, it might just make the recovery even longer. So reinforcement learning seems something that is very much used in control problems and machine learning, but it's probably not the best solution for us. So as another approach that we are trying to work on is to tackle this as a nonlinear state estimator problem. So we have a problem where we can read out a set of signals from our detector that are nonlinear function of the state of the system. So if they were linear function of the state of the system, there are standard techniques like the Kalman filter, for example, to estimate the state in an optimal way. In the case of a nonlinear system, there's not such a thing as an optimal state estimator. So the idea is that can we use, for example, a deep neural network to take the past history of our optical signals and try to reproduce the actual state of the system. The problem here is that this also cannot be implemented in an easy way on the real system because although we have the measurement of the optical signals, we don't have the target for the learning process because we don't know what their actual real degrees of freedom positions are. Because if we had them, then there would be no problem to solve. So the idea here is to start by doing this in simulation. So our models are reasonably good to simulate the direct problem. So from the simulated motion of the mirrors, what are the simulated error signals? And then the machine learning algorithm, the deep neural network in this case, will try to solve the inverse problem. So going from the measurement signals back to predict the actual motion of the mirrors. And this has been tried in simulation. You can see this graph here for a simplified model where there's a simplified interferometer. In simulation seems to be able to reproduce reasonably well the results. So the idea at the end would be that you have a sort of cycle here. So you start with a model of your system that is the best model you have at that point. And this is the direct problem. So you simulate some state evolution, and then you get the simulated output, and then you train a machine learning algorithm to solve the inverse problem, and so to predict the state given the output. And then you can essentially deploy these on the physical system, on the real system, when at this point you don't know the state, but you have an observable output. And then you can see how well the machine learning algorithm you trained in simulation can reproduce the behavior of the physical system. And if you want, once you have this, you can iterate and then improve the model by just going around this circle. And then when you're happy enough, you could be able to deploy. So this is an idea of using as much knowledge as we have of the model, and then see how much we can learn, how good machine learning algorithm is on the simulated data. There are a few technical difficulties here because we are dealing with time series. So as I mentioned many times, we need some sort of memory of what happened in the past. So this animation you should be able to see here show a simulated motion of a simple 2 degrees of freedom system, which is a power cycle microinterferometer. So there's some seismic trajectory moving around, and you can see that the 4 panels down there are simulations of the 5 optical signals that we can measure. And you can see that for a long fraction of the time, the signals are almost all close around 0. You don't have a lot of information. So that's why your neural network system needs to be able to remember the previous few seconds to interpolate between times where there isn't a lot of information from the sequence. And this is a problem because we have a sampling issue here, because at the same time, you need to track long history, let's say 2 or 3 seconds. But as you can see from this simulation here, when you cross one of the resonances, so you cross one of the points where you actually have useful information, the crossing can be very fast. So it can be order of milliseconds. And so you need a high sampling rate to be able to capture all the information you have there. So you end up with a machine learning or a neural network system that needs to handle as input training examples that can easily have thousands of samples. And this is a problem. So the standard for dealing with time series is recurrent neural network, and they're well known to not scale very well to such long time series. And the same issues, of course, is true for if you want to apply some sort of recurrent neural network, either to a reinforcement learning approach or to this supervised state estimator approach. So this is still work in progress because we haven't really found a good way around this. So we may need to apply more sophisticated ways. For example, attention mechanism might be interesting, multi-rate, or maybe completely give up the recurrent neural network and move toward convolution neural network. Particular temporal convolution neural network seems to be an interesting an interesting tool to be used here. And this is pretty much where the situation is right now. So it's really work in progress, but it seems that there is some hints that this approach might be working, might be useful. So let me now move to the second part when there are a little bit more positive results. So what can we do when we are in the high sensitivity operation configuration? So here, to give you an idea of how complicated the problem still is that so the ground moves something of the order of 10 to the 10 or even more than that times that the actual sensitivity we want to reach. So our feedback systems need to compensate for order of a few microns of motion below and a few hertz without introducing any spurious displacement larger than something 10 to the minus 19 meters above 10 hertz. So it's a very difficult problem. And you can imagine that any deviation from a linear behavior, even at a part per million, is really relevant here because we are talking about gaining 10 order of magnitudes in reduction of the motion. So it's a complex problem, but again, why do we care about this or why do we need it? So Jenny already explained a lot of this yesterday, so let me just explain the same thing in a slightly different way. So this, the larger plot you see here on the left is again the sensitivity of one of our LIGO detector. So in blue, you have the actual sensitivity measured during the last run. And in orange, the curve here is an estimate of what the sensitivity should be if we had only fundamental noises. So if you were limited by simply thermal noise and quantum noise, or stuff that is really fundamental in some sense. So you see that this red region here below something like 60 hertz is the gap. So how much worse we are with respect to what we could and would like to do. So a part of this, as Jenny mentioned yesterday, is understood as control noise. Some part of this is not really understood and we don't know exactly what it is. This is, the small inset here shows you how much we are losing in terms of range as a function of the mass of the binary system that we are trying to detect. So you can see that for system with a component mass around 100 solar masses, we are losing a significant fraction of the range. Most interesting than that, those plots here shows for different masses of 10, 50, or 100 to 100 solar masses, what is the integrand of the SNR? So how much signal-to-noise ratio you are accumulating at every frequency. And you see that in all cases, so the solid curves here is with the actual sensitivity, and the lines gives you what we would have if we were limited only by fundamental noises. So you can see that we are losing a lot of signal-to-noise ratio at low frequency, which means that we are losing the early on orbits of those binary systems. So if we were able to reduce the sensitivity, not only we increase the range, but we were also probably able to detect those systems earlier on. So this is even more interesting in terms of multi-messenger astronomy, of course. So the point here is, what can we do here? How can we improve this sensitivity? So some of these noise, as I said, can be understood and can probably be removed using approaches based on machine learning and data mining. Because during operation, the typical LIGO detector saves order of 4,000 different monitoring channels. So we don't save only the main gravitational wave strain, but a lot of more channels. So this is something on the order 1.6 gigabytes per minute. So it's a lot of stuff. So we are going into the regime of having big data and having to find efficient ways to actually mine that data and to get some information out. So if the system, if the interferometer were absolutely linear, then we know we have ways to study linear couplings of noises into the detector sensitivity, and we know how to find them, and we know how to subtract the noise. And this has been done many times. There are a few examples here of both online and offline subtraction of some noise that was witnessed by auxiliary channels that was identified because of the experience of the commissioners, or because we were looking at the frequency domain coherence between the main gravitational wave strain and the auxiliary channels. And that this could be subtracted either using some sort of linear filter offline or using some feed-forward techniques in the online system. So the point here is that the coupling of the noise from auxiliary channels to the main sensitivity is linear and stationary. We know how to tackle it. We have techniques, for example, we can compute the coherence of the gravitational wave strain with everything we have recorded on disk and find suitable channels that might be interesting for noise subtraction. And then we know how to do either offline or online noise subtraction. The problem is more complex when there is non-linear or non-stationary coupling from the auxiliary channels to the main gravitational wave channel. Of course, the most general non-linear noise coupling is some sort of functional that will take past history of a bunch of signals and then convert them in some noise that couples into the HFT, into the gravitational wave strain. And of course, this can be the most general function with the only requirement to be causal, so that to depend only on the past. Of course, we can do much if this is all we can do. The point is that the fact that our feedback system are working as hard as possible to maintain the system close to the linear operation means that in most cases, we expect only small deviation from linearity. So we expect things like quadratic couplings or non-stationary couplings. And so some examples are shown here. On the left, you see a quiet period of time, and then on purpose, we injected some noise in one of the auxiliary longitudinal degrees of freedom. And these spectrograms, so as a function of time, you see that the although the noise that we injected was stationary, the effect on the sensitivity was not stationary, because sometimes the noise was coupled with lower or with higher intensity. Another way of looking at this is, for example, what is shown here on the right. So this is an example of how the main power line and harmonic at 60 Hertz, so from the main power supply, how it couples into the detector sensitivity. You would expect that to be just polluting your sensitivity at 60 Hertz, but actually you see some modulation sidebands around here, which are another way of saying that the main 60 Hertz line is coupling with a transfer function which is not completely constant into time, but can vary over a time scale of fractions of a second over a few seconds. And so the result seen in frequency domain is, if you want, the convolution of the single line with the modulation, and so this kind of sidebands here. So how can we, so knowing that in many cases the noise couples in a non-stationary way like this, how can we try to tackle this? So the idea is that here, instead of trying to solve for the most general non-stationary or non-linear behavior, we simplify and we put into our machine learning model as much of physics knowledge as we can. And so we assume that we have signals that witness our fast noise, so stuff between 10 and 200 Hertz. Thinking, for example, of the 60 Hertz, a monitor of the power supply that will see the 60 Hertz. And then we have other signals that can witness the modulation. So they have a contained interesting signals on the very low frequency, let's say below 1 Hertz, and they are witnessing the modulation. So you can start from the most general nonlinear coupling, apply this simplification, expand your system in Volterra series if you want to go fancy with mathematics, and you figure out that the most general case can be expressed by something which is relatively simple. So your target strain has a contribution, of course, coming from linear and stationary coupling, plus a contribution of a bunch of transfer functions, linear and stationary transfer functions, that takes as input the time domain product of your fast noise witness and the modulation witness. And the fact that you have a time product there is really a result of this idea that you split the frequency content of the signal. So the noise is witnessed by a bunch of channels and the modulation is witnessed by other channels. So the advantage of this is that then you can parameterize the transfer function with a very low number of parameters, and then you can use machine learning inspired algorithms to try to find the optimal parameters. And this turned out to be quite successful. So this left plot here shows the same example I was showing earlier with the spectrogram. So we started from the quiet condition, it is the orange curve, and then we injected a lot of signal cycling cavity length noise, so one of the auxiliary length degrees of freedom. If we try to do only a stationary and linear subtraction, we could get from the blue curve only down to this green curve. If we allow for modulation with a series of signals that we think are useful for modulation, we can improve quite a lot on the stationary subtraction and get down to the red, which is not quite yet as good as the orange curve here. And the reason being that we didn't capture all of the modulation. But it's just a proof of principle that going from a stationary subtraction to a non-stationary subtraction, you can improve by almost a factor of 10 in some places. Similarly, the other example that was showing this 60 Hertz power line and harmonics shows you how much you can improve. So the blue curve is exactly the same as before. Then if you only do a stationary subtraction, as expected, you can only get rid of the line at 60 Hertz. So you get to this orange curve, which is the same as the blue almost everywhere except at 60 Hertz. But the non-stationary subtraction is able to capture additional modulations. It's able to get rid of all these sidebands. So the background you get on this red curve is significantly improved with respect to the linear subtraction. So this is just to give you an idea that this kind of physics-informed machine learning model based on non-stationary modulation is probably, it's clearly not the most general non-linear coupling you can imagine, but it's still good enough to improve the trans LIGO sensitivity. And the advantage is that it gives you interpretable results because you can look at the coefficient and learn what is the signal, the degree of freedom that really modulate the couplings. And also it is intrinsically causal and intrinsically in time domain. So you gives you directly coefficient that you can deploy from the offline subtraction to online and run it in the system without really any change. This is also being applied to O3 data, and just to go back on that big gap at low frequency between where we could be and where we are, this kind of non-stationary and stable noise subtraction can get you from this blue curve to this orange curve by subtracting longitudinal and angular control noise. So this is something we are producing for all of the last science data. So it's not quite going all the way down to fundamental noises, but this is also an iterative approach. So you can subtract some noise and then see if you can get something more after that. So it's a very promising approach, I believe. So of course, we are talking about machine learning. So the question that some of you might ask is, why not using a neural network? Because in theory, a deep neural network could be able to express arbitrarily complex nonlinear functions. So if you were able to, if you just use a neural network instead of my simplified model, this could be able to capture the most general nonlinear model, given you have enough complexity. The problem again is that we need to include time dependency and the history of the past behavior of the signals. And we have to put together, as in the example I showed, the ability of the neural network to capture the noise around 100 hertz or 60 hertz, but also at the same time to capture modulation at a fraction of a hertz. And then we're back again on this problem of needing fast sampling and long history. And so both convolutional neural network and recurrent neural network do not scale very well because they're typically hard to train. And in the experiment that has been done, it has been found, for example, that a neural network can be trained to do the same linear noise subtraction that I was showing earlier, but it typically underperforms the result with respect to the simplified model I was showing in other examples, for example, this signal noise recycling subtraction. Then, of course, there's one more point, is that neural network is still sort of a black box. So it's very hard to interpret the result. So it's hard to look at what the network learned and have some information that can be useful to improve the real detector in the real system. So that's why so far neural networks have not been as successful as other models to subtract noise. So, of course, all of this relies on the fact that somebody, the commissioners or some data analysis people, looked at the sensitivity and decided that it was a good idea to try to subtract that particularly channel as a noise monitor and using that particular set of channels as modulations. How can we look at all that data, that 1.6 gigabyte per minute of data that our detector produce, and try to automatically, in a smart way, discover noise couplings? So in the case of a linear stationary coupling, the problem is solved. We can do what we call the brute force coherence, because if there is a linear relationship between an auxiliary channel and one of our and the gravitational wave strain, then we can compute the frequency domain coherence based on FFT transforms. And if that's close to 1, it means that there's a good probability that that auxiliary channel is witnessing noise that can be subtracted. And so the approach here is just to take some time of data and compute the coherence of the gravitational wave strain with everything. And then you can produce tables like this that for every single frequency gives you a list of which are the auxiliary channels that are the most coherent with the gravitational wave strain at that frequency. And then you go from having 4,000 channels of only a few of them, and then you can start doing some attempt on noise subtraction. What can we do in the nonlinear case? Well, of course, I don't think if there is really a way to look through order of 4,000 channels and look for the most general nonlinear noise coupling. That's complicated. Even if we restrict to only quadratic couplings, which is probably already a step forward, then you have to, a brute force approach doesn't really scale very well, because you're gonna have to look at 4,000 squares, so 16 million channels, which starts to be too much. And then the point is that how do you actually assess if there is some nonlinear quadratic relation between those channels? You could use big pi coherence, which is, I know, coherence that is an extension with quadratic phase relation between signals, but this is computationally really too expensive. So far, it has been successful to use some reduced scope approaches. So for example, if you select a few channels that have content on a low frequency and that you know they're useful for detect modulations of coupling, for example, angular fluctuation on the positions of the mirrors or detector, then you could use them in a sort of brute force coherence-based approach that is able to capture not only the linear relationships, but also the modulated relationship in the sense of the equation that I showed a few slides ago. And this plot here shows an example how if we had this tool at the time, we were looking at the 60 hertz subtracting noise around the 60 hertz harmonic, we would find that there is high coherence at 60 hertz with an unmodulated channels. But then if you modulate the power supply monitor with angular controls, you actually see coherence at the sidebands around it. And this predicts also that you could get rid of noise at those frequencies. So this is a tool that could be used for a sort of a reduced scope searches for modulated channels. So you have to pick some candidates for modulation, and then you can do a brute force approach with all the possible channels. So let me move to the conclusions and wrap up with what I try to tell you today. So I think that a machine learning approach can have quite an impact on the control and the noise subtraction in our detector. And again, I discussed those two broadly different approaches, states, if you want. First, the lock acquisition, which is a nonlinear control problem. This has the potential to reduce the instrument downtime. So this is also useful. Of course, we need to find a way to make good use of all the models we have and refine them using data from the detector, because time on the real machine is really expensive and limited. So the more we can develop techniques offline and then deploy them online, the better. The problem here is that we are dealing with long-time series. So neural network approaches like recurrent neural network, they perform poorly. So we need some alternatives. For example, temporal convolutional networks looks very, very promising. So there's a lot of work going on and a lot of research trying to implement machine learning approaches for this nonlinear control problem. Of course, machine learning isn't the only approach. There are modern control techniques that are used already a lot out there in the world, outside of the gravitational wave field, for the control of nonlinear system, from the extended Kalman filtering, which is just a sort of approximation for nonlinear system, to a lot of other model-based predictive control techniques. For example, something that seems promising is some sort of a state estimation based on Bayesian filtering and Bayesian estimation. But I don't have time to talk much about that. On the other hand, the other regime is this noise subtraction that can be used to improve online and offline our sensitivity of our detector. And here we had quite some success by not quite trying to deploy the most general nonlinear neural network, but trying to put in the model we are trying to train as much information about our detector as we have. And I think this is a key here. More physics knowledge we put into our machine learning algorithm, the better they perform and the less risky it is that they're gonna do something very bad with our data. The problem is, of course, how can we move beyond just guessing what are the good channels and discover noise couplings efficiently? And here we have a lot of data, and if we had infinite computational power, we could do that, but we don't. So it's important to try and figure out an efficient way to discover noise coupling. That's all I have. I thank you for your attention, and I'll be happy to answer any questions.